Now in this lecture I answer two questions. In the first question you find out the radius of this circle. In the second question you find out the area of this green shell. So let's start with the first question. In the drawing we have quadrilateral ABCD that is inscribed by this circle. Side AD of this quadrilateral ABCD equals to 6 units in its length. Side AB equals to 4 units in its length. Side CD equals to 5 units in its length. This is side BC is equals to 4 units in its length. Okay, our task is to find out the radius of this circle. So first of all, we define this angle BCD as alpha. Therefore, the opposite angle BAD must be equal to 180 degrees minus alpha. Why? Because of the fact that 180 degrees minus alpha plus alpha is equal to 180 degrees. That is the sum of those two opposite angles inside the cyclic quadrilateral ABCD. So repeat according to rule 22. Repeat rule 22. According to rule 22, the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. In the drawing, the quadrilateral ABCD that is guided by this circle. The sum of those two opposite angles is equal to 180 degrees. That is to say, A plus B equals to 180 degrees. Likewise, the sum of those two opposite angles is also equal to 180 degrees. That is to say, x plus y equals to 180 degrees. So we already implemented rule 22 in our drawing. This angle equals to alpha according to our definition. Therefore, this opposite angle BAD must be equal to 180 degrees minus alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of those two opposite angles inside the cyclic quadrilateral ABCD. Therefore, this angle must be equal to 180 degrees minus alpha according to rule 22. In the next step, we will join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. This is the first part. The first part is actually the upper triangle ABD, the upper great triangle ABD. The second part of quadrilateral ABCD is this part, is actually the lower triangle BDC. So in the next step, we will implement the law of cosines of both triangles, in the great triangle and the lower triangle BDC. So a principle of the law of cosines. First of all, the law of cosines is true in any triangle. This is triangle ABC that could be any triangle. This is angle BAC that is equal to theta degrees in size. This is side AB of triangle ABC that is equal to A units in its length. This is side AC that is equal to B units in its length. This is side BC that is equal to C units in its length. So in this triangle ABC that could be any triangle, according to the law of cosines, the following equation is true. C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square. C square equals to A square plus B square minus 2 times A times B times cosine theta. So the first step, we will implement the law of cosines on this green triangle ABD. So according to the law of cosines, triangle ABD. The following equation is true. BD square equals to AD square plus AB square minus 2 times AB times AD times cosine 100 degrees minus alpha. And again, this grand triangle ABD according to the law of cosines. The following equation is true. BD square equals to AD square plus AB square minus 2 times AD times AB times cosine 100 degrees minus alpha. This is equation 1. This is equation 1. That is the implementation of the law of cosines of this grand triangle ABD. We have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha. So we can actually substitute cosine 180 degrees minus alpha. We can substitute cosine 180 degrees minus alpha in this equation 1 by minus cosine alpha. We do it now and get that cosine 180 degrees minus alpha equals to minus cosine alpha according to this trigonometric identity. And in total, if you found out that BD square equals to AD square. AD is 6, therefore AD square is 6 squared, that is 36. Plus AB square. AB is 3, therefore AB square is 3 squared, that is 9. And we have also minus 2 times AD is 6 times AB is 3 times cosine alpha. And cosine alpha times cosine 100 degrees minus alpha. And cosine 100 degrees minus alpha is minus cosine alpha according to this trigonometric identity. So this expression in the green color, we have minus times minus is plus. So in total this expression is a positive expression. The value of this positive expression is plus 2 times 6 is 12, 12 times 2 is 36, so it is plus 36 times cosine alpha. So in total, we found out that according to equation 1, BD square equals to 36 plus 9 is 45, plus 36 times cosine alpha. Repeat again, in total, according to equation 1, we actually found out that BD square equals to 45 plus 36 times cosine alpha. In the next step, we will implement the law of cosines in this lower triangle, triangle BDC. According to the law of cosines, this lower triangle, triangle BDC, the following equation is true. This will be equation 2. BD square equals to CD square plus BC square plus 2 times CD times BC times cosine alpha. And again, put according to equation 2. In this lower triangle BDC, according to the law of cosines, the following equation is true. BD square equals to CD square plus BC square minus 2 times CD times BC times cosine alpha. So BD square, BD is the missing side, so limit is CD, so it is BD square equals to CD square. CD is 5, therefore CD square is 5 squared, this is 25. Plus BC square. BC is 4, therefore BC square is 4 squared, it is 16. Minus 2 times CD is 5, times BC is 4, times cosine alpha. So total according to equation 2, we found out that BD square equals to 25 plus 16, plus 2 times 5 times 4 times cosine alpha. So BD square equals to 25 plus 16 is 41, and we have here minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40, so total this expression equals to minus 40 times cosine alpha. So total according to equation 2, if you want to know that BD square equals to 41 minus 40 times cosine alpha. This is according to equation 2. Well, according to equation 1, we already found out that BD square equals to 45 plus 36 times cosine alpha. So here we have two equations for BD square, equation 1 and equation 2. Therefore, we will get equation 3 that states that BD square according to equation 1 must be equal to BD square according to equation 2. Very simple equation. BD square according to equation 1 equals to 45 plus 36 times cosine alpha. It must be equal to BD square according to equation 2. BD square according to equation 2 equals to 41 minus 40 times cosine alpha. So here we subtract 41 from this equation, equation 1. So here 41 will get cancelled. This side of the equation we have to leave minus 40 times cosine alpha. While on the other side of this equation 3, you have 45 plus 41 is 4 plus 36 times cosine alpha. So total according to equation 3, we found out that 4 plus 36 times cosine alpha equals to minus 40 times cosine alpha. So here we add 40 times cosine alpha to this equation, equation 3. And we get according to equation 3, 40 times cosine alpha minus 40 times cosine alpha is 0, so here, minus 40 times cosine alpha we get cancelled, we left with nothing, that This is to say 0. This side of the equation 3, and on the other side of the equation 3, we have 4 plus 40 times cosine alpha plus 36 cosine alpha is 76 times cosine alpha. So the total according to equation 3, if you found out that 4 plus 76 cosine alpha equals to 0. So here we subtract 4 from this equation 3. Here according to equation 3. Here 4 you get cancelled. So in this side of equation 3 we left only with 76 times cosine alpha, and on the other side of equation 3 we have 0 minus 4 is minus 4. So total according to equation 3, we found out that 76 times cosine alpha equals to minus 4. Here we divide this equation 3 by 76. Again, according to equation 3, cosine alpha equals to minus 4 over 76. Minus 4 over 76 equals to minus 0.0526. So total found out that according to equation 3, cosine alpha equals to minus 0.0526. Repeat again, according to equation 3, we found out that cosine alpha equals to minus 0.0526. We would like to find the value of alpha itself. In order to find the value of angle alpha itself, we have to operate the opposite function of cosine, or the result of cosine alpha is actually minus 0.0526. In this way we get the value of alpha itself. So we operate the inverse function of cosine, that is inverse cosine, or the result of cosine alpha is actually 0.0526, and this will give us the value of alpha itself. So if you operate the inverse function of cosine on minus 0.0526, you find out that the result is 93.017 degrees. Equals to alpha. So we found out that the size of angle alpha is equal to 93.017 degrees in its size. This is angle alpha is equal to 93.017 degrees. What is the value of BD? According to equation 2, we only found out that BD square equals to 41 minus 40 times cosine alpha. Now we can substitute alpha by 93.017 degrees. We'll do it now. We get that BD square according to equation 2 equals to 41 minus 40 times cosine alpha. So it is 40 times cosine alpha 93.017 degrees. So total according to the equation 2, if you found out that BD square equals to 41 minus 40 times cosine 93.017 degrees. Actually, the value of this expression, that is to say, minus 40 times cosine 93.017 degrees, in total this is equal to plus 2.105. 2.105. So total we found out that BD square equals to 41 plus 2.105. So BD square equals to 41 plus 2.105 is 43.105. So here we take out of this equation 2, and get that according to equation 2, BD equals to the square root of 43.105 is equals to 6.565 units in Islam. So again, to that we found out that the length of this side BD is equal to 6.565 units. In the next step, we will implement the law of sines in its full version of this lower target BDC. And again, we will implement the law of sines in its full version of this lower target BDC. So a quick description of the law of sines. The law of sines is true in any triangle. So this is a triangle ABC that could be any triangle. This angle BAC is equal to capital A divided inside. This angle ABC is equal to capital B divided inside. And finally this angle ACB is equal to capital C divided inside. In addition, we know that side AB equals to C units in its left, side AC equals to B units in its left, side BC equals to A units in its left. And triangle ABC is described by this circle. The radius of this circle is R. So, according to the law of sines in its full version, the following equation is true. Now drawing. A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And now is the radius of this circle that blocks triangle ABC. And again, according to the law of sines in its full version, in our drawing, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And again, R is the radius of this circle that blocks triangle ABC. So can actually implement the law of sines in its full version in our triangle BDC. On our triangle BDC. Why? Because of the fact that triangle BDC is described by this circle. Why triangle BDC is described? Why triangle ABC is described by this circle? Because of the fact that all the vertices of this triangle BDC, that is to say D, B, and C, lie on the circle itself. So, we'll implement the law of sines in its solution of this triangle BDC that is described by this circle. According to the law of sines in its solution, we get that BD over sinus alpha equals to 2R. Again, BD equals alpha equals to 2R. And R is the radius of this circle that involves triangle ABC, or triangle ABC is inscribed on this circle. R is also the radius that we're looking for in this question. BD equals to 6.565. Sinus alpha. Alpha equals to 93.017 degrees. So it is sinus 93.07 degrees. Equals to 2R. So those are found on the BD of sinus alpha equals to 2R. BD is 6.565. Alpha is 93.017 degrees. So total BD over sinus alpha is 6.565 over sinus 93.017 degrees equals to 2R. And now is the radius of this circle that we are looking for. Actually, the value of this expression, the green color, the value of this expression in total is equal to 6.5745. Okay. Those two sides of the equation are equal to each other. That is to say, 6.745 equals to 2R. Total expression ordered 6.5745 equals to 2R. Here we divide this equation by 2 and find that R equals to 6.745 over 2 is 3.287 units. And that is the answer to the question. This is to say, if we found out that the radius of this circle, that is the radius that we are looking for in this question, is equal to 3.287 units in its length. So we finished to answer on the first question. The next step I present to the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have the big quadrilateral ABCD. It is given us the question that line segment AP equals to line segment PB in its length. We also know that side AD of this quadrilateral ABCD equals to 9 units in its length, side DC equals to 8 units in its length, side BC equals to 7 units in its length. Again, our task is to find out the area of this green shape. And again, our task is to find out the area of this green shape. AB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. So if we focus on the lower side of the straight line AB at point 3, if the sum of the areas must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have the lower side of the straight line AB at point P, we have this angle, the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will join points A and Q together by straight line. Repeat again. We join points A and Q together by straight line. Likewise, we join points B and Q together by straight line. So by doing those constructions, we can do those two right triangles. We have the right triangle APQ, the right big triangle PBQ. In the next step, we will prove that those two right triangles can go into each other according to side angle side rule. So we have to prove that the right triangle APQ, the right triangle APQ, and went to this green triangle PBQ according to side angle side rule. So why those two triangles can go into each other? First of all, it is given us a question that AP equals to PB. So we can write down that side AP of the right triangle PQ is equal to side PB of the green triangle PBQ. And again, side AP of the right triangle equals to side PB of the green triangle according to what is given us the question. In addition, those two angles are both right angles and therefore they are equal to each other. So here this is angle APQ on the right angle is equals to this angle, therefore angle BPQ on the green triangle. And again, so that we should find out that angle APQ of the right triangle equals to angle PBQ of the green triangle. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side PQ. This is the common side that belongs to both triangles. So we can write down that PQ equals to itself as a common side that belongs to both triangles. And again, PQ equals to itself as a common side that belongs to both triangles. So in total, we found out that the right side APQ congruent. This is the sign of congruent to the green triangle PBQ according to side angle side rule. This is to say, I found out that those two sides and the angle that is included between those two sides in this right triangle are corresponding equal to those two sides and the angle that is included between those two sides in this green right triangle. Therefore, those two right triangles can go into each other according to side angle side rule. Repeat again, we have those two sides and the angle that is included between those two sides in this right triangle are corresponding equal to those two sides and the angle that is included between those two sides in this green triangle. Therefore, those two right triangles can go into each other according to side angle side rule. The right triangle APQ can go into the right triangle PBQ according to side angle side rule. And for the fact that those two right triangles can go into each other, we derive that they must have also the same areas. This is to say they have the right triangle APQ as we come to the green triangle PBQ. This is the first thing that we will derive. that the area of the white triangle APQ is equal to the area of the green triangle, triangle PBQ. Because of the fact that any two triangles that can go into each other, they must have also the same area. So if you define the size of the area of the green triangle PBQ as A, that is to say, the size of this green triangle equals to A square units, according to our definition. Then the size of this triangle APQ must be equal to A square units. Why? Because they are equal to each other in their sizes. It's simple. What is the definition of quadrilateral ABCD? Because of the fact that the sum of those two one-sided interrogants is equal to 180 degrees, then according to rule 20, they must be located between parallel lines. That is to say, AD is parallel to BC. So I put quickly on rule 20. According to rule 20, if the sum of two one-sided interrogants is equal to 180 degrees, then they must be located between parallel lines. So in the drawing we have line A, that is line B, this is the red transversal C that cuts those two lines at those 2 points. Those two angles are both defined as one-sided interrogants. So if the sum of those two one-sided interrogants is equal to 180 degrees, then they must be located between parallel lines. That is to say, if alpha plus beta equals to 180 degrees, then line A must be parallel to line B. Likewise, if the sum of those two one-sided interrogants is equal to 180 degrees, then they must be located between parallel lines. That is to say, if gamma plus delta equals to 180 degrees, then line A is parallel to line B. So actually, we already implemented rule 20 in our drawing. Why? Because of the fact that the sum of those two one-sided interrogants is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AD is parallel to BC. So in total, if you found out that in quadrilateral ABCD we have one pair of parallel sides. Because AD is parallel to BC, any quadrilateral that has one pair of parallel sides is defined as a trapezoid. So in total, you can conclude that quadrilateral ABCD is a trapezoid. Because it has one pair of parallel sides. So you know, in total, I found out that quadrilateral ABCD is a trapezoid. Why? Because it has one pair of parallel sides. The second thing that we conclude from the fact that those two triangles can go into each other, we know that their hypotenuses must be equal to each other in their lengths. That is to say, AQ equals to BQ. Why AQ equals to BQ? AQ equals to BQ according to the rule that corresponding sides that can right triangles are equal to each other. Those two right triangles can go into each other, therefore their corresponding sides, that is to say AQ and BQ, must be also equal to each other in their lengths. So in total, if you found out that AQ equals to BQ, you square this equation, you get that AQ squared equals to BQ squared. Here we can implement the Pythagoras theorem on our domain. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendicular. So again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. So in this right triangle ADQ, according to the Pythagoras theorem, we get that AQ square equals to AD square plus DQ square. AQ square equals to AD square plus DQ square. Therefore, we can substitute AQ square by AD square plus DQ square in this equation 2. AQ square equals to AD square plus DQ square. This right triangle ADQ. And we have AQ square equals to BQ square. BQ is the hypotenuse of the green right triangle BQC. So according to the Pythagoras theorem, in this green right triangle BQC, we get that BQ square, that is the square of the hypotenuse, equals to BC square plus CQ square. Again, BQ square equals to BC square plus CQ square. Therefore, we can substitute BQ square, this equation 2, by BC square plus CQ square. And again, we substitute BQ square in this equation 2 by BC square plus CQ square. So in total, if you want to according to equation 2, AD square plus DQ square equals to BC square plus CQ square. We define the length of side DQ on this side ADQ is x. What is the value of QC? QC equals to DC minus DQ. Write it down. QC equals to DC minus DQ. So QC in total equals to BC. BC is 8 according to what is the question. Minus DQ. DQ is x according to our definition. So in total, we found out that QC equals to 8 minus x units in itself. We will continue with equation 2. According to equation 2, we found out that AD square plus DQ square equals to BC square plus CQ square. AD is 9, therefore this square is 9 squared, that is 81, plus DQ square. DQ is x, therefore DQ square is x square. And it's equals to BC square. BC is 7, therefore BC square is 7 squared, that is 49. Plus QC square. QC is 8 minus x, therefore QC square is 8 minus x square. So in total, according to equation 2, we actually found out that 81 plus x square equals to 49 plus 8 minus x square. So 81 plus x square equals to 49 plus 8 minus x square. Here we'll open the brackets of this expression according to the algebraic identity that says that a minus b square equals to a square plus b square minus 2 times a times b. And get that 8 minus x square equals to 8 squared, that is 64, plus x squared minus 2 times 8 times x, that is minus 16x. So here we have x squared on both sides of this equation. So x squared gets cancelled. After I cancel x squared, on this side of equation 2 we left only with 81, while on the other side of equation 2 we have 49 plus 64 is 113 minus 16x. So in total, according to equation 2, we found out that 81 equals to 113 minus 16x. So here we get 16x, so this equation 2. So in this is equation 2, 16x will get cancelled, we left only if 113, this side of the equation, and on the other side of the equation we have 16x plus 81 equals to 113. So return equation in new page. So according to equation 2, if you found in total that 81 plus 16x equals to 113. Here we subtract 81 from this equation 2. Get according to equation 2, here 81 again cancelled. This side of the equation we have only 16x, while on the other side of equation 2 we have 113 minus 81 is 32. So in total, if you want to know that 16x equals to 32, here we divide this equation 2 by 16, and finally get that according to equation 2, x equals to 32 over 16 is 2. X equals to 2 units in its length. This is side dq equals to x and x equals to 2. So dq equals to 2. Likewise, side qc side qc equals to 8 minus x. 8 minus x is 8 minus 2, that is 6. So qc in total equals to 6 units in its length. We already found out that quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. Quadrilateral ABCD is a trapezoid. But what is the area of trapezoid ABCD? Actually, we have a special formula for the area of any trapezoid. This is trapezoid ABCD. AB is parallel to CD. The length of AB is A units, CD equals to B units in its length. Those two parallel sides are defined as the bases of the trapezoid. So the area of this trapezoid ABCD equals to the sum of its two parallel bases, that's actually A plus B times the height edge over 2. And again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that's actually A plus B times the height edge over 2. The height edge must create the rest with the two parallel bases. Here you can see that edge creates an address with this base and edge also creates an address with the base AB. So in total the area of trapezoid ABCD equals to the sum of its two parallel bases, to say in this case it is A plus B times the height edge over 2. So we can implement the new formula in order to find out the area of our trapezoid ABCD. So according to the new formula, the area of trapezoid ABCD must be equal to the sum of its two parallel bases the two parallel bases are AD and BC. So it is AD plus BC. Times the height. The height must create an address the two parallel bases. DC creates an integral the two parallel bases, therefore the height is DC over 2. So in total, if you want to know that the area of trapezoid ABCD equals to the sum of its two parallel bases, that's AD plus BC times the height DC over 2. AD is 9 plus BC is 7 times the height DC is 8 over 2. So in total, we found out that the area of this trapezoid ABCD equals to 9 plus 7 times 8 over 2. 9 plus 7 is 16. 8 over 2 is 4. So in total, this expression equals to 16 times 4. That is 64. In conclusion, we found out that the area of trapezoid ABCD, according to the first method of calculation, is equal to 64 square inches in size. The area of this trapezoid ABCD is equal to 64 square inches in size. But we have another way to find out the area of the same trapezoid ABCD. So according to the second method of calculation, they are the same trapezoid ABCD. It must be equal to the sum of the areas of those four components that it consists of. In total, polynomial ABCD consists of four components. 1, 2, 3, 4. So the sum of the areas of those four components must be equal to the big trapezoid ABCD. Very simple. The first component is triangle ADQ. Therefore, it is the area of the right triangle ADQ. Of the first component, is the area of the right triangle ADQ, plus the area of the second component that trapezoid ABCD consists of. The second component is the right triangle APQ. So it is the area of the right triangle APQ, but according to our definition, the area of this triangle APQ is A. So the area of the second component is A, plus the area of the first component that trapezoid ABCD consists of. It is also A. This is plus A, plus the area of the fourth component that trapezoid ABCD consists of. The fourth component is this right triangle BQC. The area of this right triangle BQC so in total, if you follow that, according to the second method of calculation, the area of trapezoid ABCD must be equal to the sum of the areas of those four components that it consists of. What is the area of the first component? The area of the first component is the area of this right triangle ADQ. The area of the right triangle ADQ equals to the base, that is 2, times the height 9 over 2. 9 times 2 over 2 is 9. So in total, if you want that the area of the first component that it consists of is 9 square inches in size. The area of the first, the second component is A. The area of the fourth component is also A. What is the area of the fourth component that ABCD consists of? Actually, the area of this green right triangle QCB. The area of this green right triangle QCB equals to the base, that is 6, times the height 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So in total, if you found out that the area of the fourth component that trapezoid ABCD consists of is equal to 21 square inches in size. So the area of the first component is 9 square units, plus the area of the third component that is A, plus the area of the third component that is also A, plus the area of the fourth component that basically consists of is actually 21. So in total, the area of trapezoid ABCD equals to 9 plus 21 is 30, A plus A is 2A. So according to the second method of calculation, the area of trapezoid ABCD equals to 30 plus 2A square units in size. So it is now the area of trapezoid ABCD according to the second method of calculation is equal to 30 plus 2A square units in size. And according to the first method of calculation, we actually found out that the area of the self trapezoid ABCD is equal to 64 square units in size. So we have two different equations for the area of the same trapezoid ABCD, equation 1 and equation 2. Therefore, we get equation 3 that states that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. So the area of trapezoid ABCD according to the first method of calculation equals to 64 square units in size. Must be equal to the area of the same trapezoid ABCD according to the second method of calculation. The area of trapezoid ABCD according to the second method of calculation equals to 30 plus 2A square units in size. So in total, according to equation 3, we found out that 64 equals to 30 plus 2A. Here we subtract 30 from this equation 3. So here 30 will get cancelled, and after only 2A on this side of equation 3, while on the other side of equation 3 we have 64 minus 30 is 34. So in total, according to equation 3, we found out that 64 equals to 2A, 54 equals to 2A. Here we divide this equation by 2, and find out that according to equation 3, A equals to 34 over 2 is 17. Equals to 17 square units in size. But again, if you want to know that there of this one time APQ is 8 and A is 17. Likewise, the area of this green triangle PBQ is also 8 and A is 17 square units in its size. So our task is to find out the area of this green shape. What is the area of the green shape? From the drawing, it's very easy to see that the area of the green shape in total equals to the area of this green triangle PBQ, that is A, and A is 17, plus the area of this right green triangle BQC, that is 21 square units in size. So in total, the area of the green shape equals to 17 plus 21. 17 plus 21 is 38. So in total, we found out that the area of the green shape, that is the area that we're looking for this question, equal to 38 square units in size. And that is the answer to the second question. But again, if we found out in total that the area of this green shape, that is the area that we're looking for in this question, is equal to 38 square units in size. So we finished to answer the second question. The next step, I'll summarize the lecture. That is to say, we repeat of the solution of the first question and then we repeat of the solution of this second question. In the first question, our task is to find out the radius of this circle. So in the drawing, we have quadrilateral ABCD that is described by this circle. Of this circle blocks this quadrilateral ABCD. We know that side AD of this quadrilateral ABCD is equal to 6 units in itself, side AB equals to 4 units in itself, side DC equals to 5 units in itself, and finally side BC of this quadrilateral ABCD is equal to 4 units in itself. Again, our task is to find out the radius of this circle that blocks quadrilateral ABCD. The first step, we define angle CDB, this angle is alpha. Therefore, this opposite angle must be equal to 180 degrees minus alpha. Or because 180 degrees minus alpha plus alpha is equal to 180 degrees, that is the sum of the angles, that is the sum of those two opposite angles of the cyclic quadrilateral ABCD, according to rule 22. So please click on rule 22. According to rule 22, the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Quadrilateral ABCD is of course a cyclic quadrilateral, so the sum of those two opposite angles must be equal to 180 degrees. That is to say, A plus B equals to 180 degrees. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. That is to say, X plus Y equals to 180 degrees. So we already implemented all 22 in our drawing. In our drawing, quadrilateral ABCD is of course a cyclic quadrilateral, therefore the sum of those two angles, the sum of those two opposite angles must be equal to 180 degrees. So alpha plus this angle in total must be equal to 180 degrees. Therefore this angle must be equal to 180 degrees minus alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. It is the sum of those two opposite angles inside this cyclic quadrilateral ABCD. Therefore this angle must be equal to 180 degrees minus alpha, according to rule 22. In the next step, we join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is the upper main triangle BD, the second part is the lower triangle BCD. So in the next step, we implemented the law of cosines of both of those two triangles. So click on the law of cosines. According to the law of cosines, the law of cosines is for an any triangle, so this is triangle ABC that equals to any triangle. This angle BAC is equal to theta degrees inside, side AB equals to A units inside, side AC equals to B units inside, side BC equals to C units inside. So this triangle ABC, that is called B triangle, according to the law of cosines, the following equation is true. C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. And C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. So can I implement the law of cosines in the main triangle ABD. According to the law of cosines, we get that BD squared equals to AB squared plus AD squared and 2 times AB times AD times cosine 180 degrees minus alpha. But again, according to the law of cosines, if we implement the law of cosines, this entire BD, we get that the following equation is true. BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. We have the trigonometric identity that says that cosine alpha is also alpha equals to minus cosine alpha. Therefore, we can solve the cosine alpha is minus alpha in this equation 1 by minus cosine alpha. So in total we get that BD squared equals to AD squared. AD is 6, therefore AD squared is 6 squared is 36 plus AB squared. AB is 3, therefore AB squared is 9. And we also minus 2 times AD is 6 times AB, that is 3 times cosine 100 degrees also alpha. Cosine 100 degrees also alpha is minus cosine alpha. So in total, if you found out that according to equation 1, BD squared equals to 36 plus 9, minus 2 times 6 times 3, and cosine 100 degrees also alpha equals to minus cosine alpha according to this trigonometric identity. So in total, if you found out that BD squared equals to 36 plus 9 is 45, minus here we have minus times minus is a plus, so this expression in the green color is a positive expression. So it is plus 2 times 6 is 12, 12 times 3 is 36, so it is 36 times cosine alpha. So total according to equation 1, we found out that BD squared equals to 45 plus 36 times cosine alpha. The next step, we implemented the law of cosines in this lower triangle, triangle BDC. According to the law of cosines in this my triangle BDC, the following equation is 2. BD squared equals to DC squared plus BC squared minus 2 times BD times DC times cosine alpha. And again, according to the law of cosines, in this lower triangle BDC, the following equation is 2. BD squared equals to CD squared plus BC squared minus 2 times CD times BC times cosine alpha. BD is the missing side, so leave it as it is, and this equals to CD squared. CD is 5, therefore CD squared is 5 squared, that is 25, plus BC squared. BC is 4, therefore BC squared is 4 squared, that is 16. So total BD squared equals to 25 plus 16, minus 2 times CD, that is 5, plus times BC, that is 4, times cosine alpha. So total BD squared equals to 25 plus 16, that is 41. We have minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40, times cosine alpha. So total, according to equation 2, if you found out that BD squared equals to 41 minus 40 times cosine alpha. This is according to equation 2, and according to equation 1, we only found out that BD squared equals to 45 plus 36 times cosine alpha. So we have two different equations for BD squared, equation 1 and equation 2. Therefore, we can do the equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. Very simple equation. BD squared according to equation 1 equals to 45 plus 36 times cosine alpha. Must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to 40 minus 41 minus 40 times cosine alpha. So here we subtract 41 from the equation 3. So here 41 gets cancelled, and you have to leave minus 40 times cosine alpha. The other side of the equation 3, we have 45 minus 41 is 4, so into this side of the equation 4, 3 we have 3 plus 4 times 36 cosine alpha equals to minus 40 times cosine alpha. So here we added 40 times cosine alpha to the equation 3, so here minus 40 times cosine alpha get cancelled, and we have to leave 0 on this side of the equation, and on the other side of the equation we have 4 plus 40 times cosine alpha plus 36 cosine alpha equals to 76 cosine alpha. So in total, according to equation 3, we found out that 4 plus 76 cosine alpha equals to 0. Here we subtracted 4 from this equation 3, we found out that here 4 we get cancelled, and therefore 76 cosine alpha equals to 0 minus 4 is 4. So in total, 0 minus 4 is minus 4. So in total, according to equation 3, we found out that 76 cosine alpha equals to minus 4. Here we divide this equation 3 by 76, and we found out that cosine alpha equals to minus 4 over 76. Minus 4 over 76 is minus 0.0526. So in total, we found out that according to equation 3, cosine alpha equals to minus 0.0526. We would like to find out the value of alpha itself. In order to find out the value of alpha itself, we have to operate the opposite function of cosine, that is inverse cosine, of the result of cosine alpha, that is minus 0.0526. In this way, we find out the value of alpha itself. And inverse cosine of minus 0.0526 equals to 93.017 degrees. So today we found out that angle alpha equals to 93.017 degrees inside. This is angle alpha that equals to 93.017 degrees inside. So what is the value of BD? BD, according to equation 2, we found out that BD square equals to 41 minus 40 times cosine alpha. So BD square equals to 41 and we have minus 40 times cosine alpha. Alpha is 93.017. So from the equation 2, we found out that BD square equals to 41 minus 40 times cosine 93.017 degrees. So total BD square equals to 41 and we have here minus cosine 93.107 degrees is equal to 2.105. So total according to equation 3, we found out that BD square equals to 41 plus 2.05. That is to say, BD square equals to 43.105. So here we took out all those equations and found out that BD equals to the square root of 43.105. That is 6.565 minutes in Israel. BD equals to 6.565 minutes in Israel. The next step, we implemented the law of sines, and this lower triangle, the law of sines in its true motion, and this lower triangle BDC. So I compare the law of sines in its true motion. According to the law of sines, this is triangle ABC that could be any triangle. This is angle BAC. This is what for capital integral inside. This is angle ECB. This is equal to capital C degrees inside. And finally, this is angle ABC. This is equal to capital B degrees inside. Sine AB equals to 6 units in Israel. Sine AC of the triangle ABC equals to B units in Israel. Sine BC equals to A units in Israel. In addition, triangle ABC is described by this circle. The radius of this circle is R. So, if we implement the law of sines now going in its solution, we get that the following equation is 2. A over sin C equals to B over sin C equals to C over sin C equals to 2R. And now the radius of this circle that draws triangle ABC. Okay, again, according to the law of sines in its solution, our going, the following equation is 2. A over sin C equals to B over sin C equals to C over sin C equals to 2R. Again, R is the radius of this circle that draws triangle ABC. So we implement the law of sines in its solution on this triangle BDC, the lower triangle BDC. According to the law of sines in the solution, this lower triangle BDC, the following equation is 2. BD over sin alpha equals to 2R, and R is the radius of this circle that draws triangle BDC. Okay, again, according to the law of sines in the solution, this triangle BDC, the following equation is 2. BD over sin alpha equals to 2R. BD is 6.565 over sin alpha, alpha is 93.107 degrees. So it is 6.565 over sin alpha, that is 93.07 degrees. So the value of this expression in the green color in total is 6.5745. Those two sides of the equation are equal to each other. This is to say 6.5745 equals to 2R. So we divide this equation by 2 and find out that R equals to 6.5745 over 2, that is 3.27 units in Israel. Repeat again, if you round out in total, the radius of this circle, that is the radius that we are looking for in this equation, is equal to 3.287 units in Israel. So finish to repeat on the first question, and next time repeat on the solution of the second question. In the second question, our task is to find out the area of this green shape. So in the drawing, we have the big quadrilateral ABCD, AP equals to PB, AD equals to 9, DC equals to 7, DC equals to 8. Again, our task is to find out the area of this green shape. So first of all, AB is one side of one another ABCD, therefore it is absolutely a straight line. So if you focus on the lower side of the straight line AB at point B, the sum of the rest must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the rest from one side of the straight line is equal to 180 degrees. So which angle we have the lower side of the straight line AB at point B? We have this angle, that is right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees inside. So in the next step, we did the construction. So again, this is the missing angle, equal to 90 degrees inside. In the next step, we did the construction, that is to say, we join points A and Q together by straight line, we join points B and Q together by straight line. When doing those constructions, we can do those two white triangles, the white triangle PQ, and the green triangle PBQ. So in the next step, we prove that those two white triangles can merge to each other according to side and side rule. So why those two white triangles can merge to each other? First of all, AP equals to PB according to what is given in the question. In addition, those two angles are both right angles and therefore are equal to each other. And finally, PQ is a constant that belongs to both triangles, so we can write down that PQ equals to itself is a constant that belongs to both triangles. So in total, we found out that the green triangle APQ can go into the white triangle APQ can go into the green triangle PBQ according to side and side rule. So again, the white triangle APQ can go, this is the side can go to the green triangle PBQ according to side and side rule. And so the fact that those two triangles can go into each other, we learned that they must have also the same areas. This is to say, they have the white triangle APQ must be equal to they have the green triangle PBQ. Why? Because of the fact that if two triangles can go into each other, they must have also the same areas. So if you find they have this green triangle PBQ as A, that they have this white triangle APQ must be equal to A because they are equal to each other, they have areas, they have the same areas. And the second thing that we will learn from the fact that those two triangles can go into each other, we will learn that AQ equals to BQ. AQ equals to BQ. Why AQ equals to BQ? AQ equals to BQ because it was all that said that corresponding sides and can go triangles are equal to each other. Those two triangles can go into each other, therefore their corresponding sides, that is to say AQ and BQ must also equal to each other and their x. So we square this equation, equation 2, found out the thing that AQ square equals to BQ square. You can implement here the Paderewski theorem in our drawing. According to the Paderewski theorem, in any right triangle, the square of the opposite equals to the sum of the sides of the perpendiculars. Again, the square of the opposite equals to the sum of the squares of the perpendiculars. So in the right triangle ADQ, AQ square equals to AD square plus DQ square. Therefore, we can substitute AQ square by AD square plus DQ square. And again, we can substitute AQ square by AD square plus DQ square. Substitute AQ square by AD square plus DQ square. It is true according to the Paderewski theorem. And AQ square equals to BQ square. So the next step, implemented the Paderewski theorem in this triangle BQAC. According to the Paderewski theorem, in this triangle BQC, the following equation is to BQ square equals to BC square plus CQ square. Again, BQ square equals to BC square plus CQ square. Therefore, we can substitute BQ square by BC square plus CQ square. And again, to know that BQ square equals to BC square plus CQ square according to the Paderewski theorem. So according to the equation 2, we shall know that AD square plus DQ square equals to BC square plus CQ square. AD is 9, therefore D square is 9 squared, that is 81. Define the length of DQ as x. Therefore QC must be equal to DC plus DQ. QC equals to DC is 8 plus DQ is x. And so QC equals to 8 minus x. So now the question we have DQ square. dq is x, therefore dq squared is x squared. So this is the equation 2. We have 81 plus x squared equals to bc squared plus cq squared. bc is 7, therefore bc squared is 7 squared, that is 49, plus q squared. Q3 is 8.6, therefore q3 squared is 8.6 squared. So total, according to the equation 2, we know that 81 plus x squared equals to 49 plus 8.6 squared. So 81 plus x squared equals to 49 plus 8.6 squared. 8.6 squared equals to 8 squared, that is 64. Plus x squared was 2 times 8 times 6, that is 116. So here we have x squared on both sides of this equation, so x squared is cancelled, so cancel x squared on this side of the equation, we have only with 81, while on the other side of the equation, we have only with 49 plus 64, that is other 13 was 16x. So total according to equation 2, we have found out that 81 equals to under 13 was 16x. So here we added 16x on this equation 2. So here 16x is cancelled. We have only found out 13, while on the other side of equation 2 we have 81 plus 16x. So total according to equation 2, we found out that 81 plus 16x equals to 113. Here we subtract the 81 from this equation and equation 2. So here 81 gets cancelled, and we have only 16x in this side of equation 2, and on the other side of equation 2 we have 113 minus 81 is 32. So total according to equation 2, we found out that 16x equals to 32. Here we divide this equation 2 by 16, and we found out that x equals to 32 over 2, x equals to, again we divided the equation by 16. So x equals to 32 over 16, this is 2, x equals to 2. Here x equals to 2, here 8 minus x equals to 8 minus 2, that is 6. So total dq equals to 2, qc equals to 6. Those two angles are defined as one-sided angles. The sum of those two one-sided angles is 180 degrees. And according to Rule 20, they must be located between parallel lines. That is to say, AD is parallel to BC. Again, because of the fact that the sum of those two one-sided angles is equal to 180 degrees, they must be located between parallel lines according to Rule 20. That is to say, AD is parallel to BC. So please click on Rule 20. According to Rule 20, if the sum of two internal one-sided angles is equal to 180 degrees, then they must be located between parallel lines. The moment we have line A, this is line B, this is the red transversal C that cuts those two lines and those 2 points. Those two angles are both defined as one-sided and triangles. So if the sum of those two one-sided angles is equal to 180 degrees, that is to say half cos beta equals to 180 degrees, then they must be located between parallel lines. Then they must be located between parallel lines. That is to say, line A is parallel to line B. Likewise, those two angles are both defined as one-sided and triangles. So if the sum of those two one-sided angles is equal to 180 degrees, that is to say if gamma plus delta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. Then when we implemented Rule 22, Rule 20, now going like, because the sum of those two one-sided angles is equal to 180 degrees. Again, the sum of those two one-sided angles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AD is parallel to BC. So in quadrilateral ABCD, AD is parallel to BC, therefore quadrilateral ABCD is a trapezoid. Because the definition of a trapezoid is a quadrilateral with one pair of parallel sides. Therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. Again, to that, the big quadrilateral ABCD is a trapezoid. What is the area of trapezoid? This is trapezoid ABCD. AB equals to A unit in itself, CD equals to B unit in itself. You know that AB is parallel to CD. The two parallel sides are defined as the bases of the trapezoid. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that's A plus B times the height edge over 2. The height edge must get the two parallel bases. H gets the with those two parallel bases. So in total, we found out that the area of trapezoid ABCD equals to the sum of its two parallel bases, is A plus B times the height edge over 2. Repeat again, the area of trapezoid ABCD equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. So according to the new formula, the area of this big trapezoid ABCD equals to the sum of its two parallel bases, that's actually AD plus BC times the height CD over 2. Why the height is CD? Because of the fact that the height CD creates 90 degrees with those two parallel bases. Those two angles are both right angles. So in total, we found out that the area of trapezoid ABCD equals to the sum of its two parallel bases is actually AD plus BC times the height CD over 2. And again, according to the second method of calculation, according to the first method of calculation, we found out that the area of the big trapezoid ABCD equals to the sum of its two parallel bases is actually AD plus BC times the height DC over 2. AD is 9, BC is 7, DC is 8. AD is 9, BC is 7, this is 8, divided by 2. 9 plus 7 is 16, and 8 over 2 is 4. So in total, this expression equals to 16 times 4. 16 times 4 is 64. So according to the first method of calculation, we found out that the area of this big trapezoid ABCD is equal to 64 square units in size. But we have another way to find out the area of this big trapezoid ABCD. It's very clear that the area of trapezoid ABCD must be equal to the sum of the areas of the components that it consists of. That is to say, the area of trapezoid ABCD must be equal to the sum of the areas of those four components that it consists of. 1, 2, 3, 4. The area of the first component is the area of this right triangle DC. The area of the right triangle DC equals to 9. The base is 2 times the height is 9 over 2. 9 times 2 over 2 is 9. So the area of the first component that trapezoid ABCD consists of is 9 square units in size. Likewise, the area of this second component is A according to our definition. Likewise, the area of the first component that trapezoid ABCD consists of is the area of this triangle PPQ. According to our definition, the area of the right triangle PPQ equals to 8 square units in size. Plus the area of the fourth component that trapezoid ABCD consists of is the area of this green right triangle BQC. The area of the green triangle BQC equals to the height and the base is QC, that is 6 times the height CB, that is 7 over 2. 6 times 7 is 42, 42 over 2 is 21. So in total, we found out that the area of the fourth component that the trapezoid ABCD consists of is 21. Again, according to the second method of calculation, the area of the same trapezoid ABCD must be equal to the sum of the areas of those four components that it consists of. This is 9 plus 8 plus 21. 9 plus 21 is 30, 8 plus 8 is 28. So in total, according to the second method of calculation, the area of the same trapezoid ABCD equals to 30 plus 2 square units in size. This is according to the first method of calculation. But according to the first method of calculation, we only found out that the area of the same trapezoid ABCD equals to 64 square units in size. So we have two different equations for the area of the same trapezoid ABCD. Therefore, we get equation 1 and equation 2. Therefore, we get equation 3 that says that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. So the area of trapezoid ABCD according to the first method of calculation equals to 64 square units in size. It must be equal to the area of the same trapezoid ABCD according to the second method of calculation. The area of trapezoid ABCD according to the second method of calculation equals to 30 plus 2a. So total according to equation 3, we found out that 64 plus 30 plus 2a. If subtracted 30 from this equation, equation 3, so if 30 gets cancelled, the left leaves 2a, while on the other side of the equation, if 64 minus 30 is 34. So in total, according to equation 3, we found out that 44 equals to 2a. Here we divide this equation by 2, and we found out that a equals to 34 over 2, and 17. So a equals to 17. Now this one triangle PQ is A and A is 17. Likewise, the area of this green triangle PQB is also N and is 17. So we found out that the area of this green triangle PCQ is 21. The area of the green shape in total equals to 17 plus 21. And we found out that the area of the green shape equals to 17 plus 21, that is 38. So total, if you found out that the area that we wrote about this question, that is the area of this green shape is equal to 38 squares in size. Okay, thank you very much.